Hey everyone, working through the textbook today. I'm starting on page M2-105. We're still working with polynomial regression. The big difference is the other day we stopped here. We graphed the points, kind of thought about which function might model those points, and then again just used our calculator to come up with that equation. The big difference today is just applying that equation to like a real world scenario and actually using the equation that we built. So to do so, we'll work through this example problem. Looks like some city planners are thinking about building a new stadium on some land close to downtown. They monitor the number of vehicles entering and exit downtown from a major highway between 1 and 7 p.m. to determine current traffic conditions. If there's too much traffic, maybe they try to build a stadium somewhere else. So it gives us all the information that they gathered. It looks like at 1 p.m., there were around 7,000 vehicles that entered and exit that highway. At 2 p.m., there's 10.8 thousand vehicles. It looks like it eventually reaches a peak at 5 p.m. and then eventually dwindles back down as we approach nighttime. So that's really how I would answer question A. Describe any patterns. It looks like we reach a peak from 4 to 6 p.m. 4 to 6, we've got a lot of traffic there. The other times of day, especially during the middle of the day, there doesn't seem to be a lot of traffic. And again, at night, it kind of starts to, after 6 p.m., it seems like it trails off pretty well. Predict the type of polynomial that best models the data. Well, one thing that can really help us out is graphing it. So if I go to my calculator, it can make a nice scatter plot for me. The first thing to do to get it to graph the scatter plot would just be hit the stat button, hit enter, and start putting this data into a list. Now, all you have to do in these lists is put the x values, which in this case is the time, in the first column, and then put your y values, or the traffic amount, in the second column. I've got all the data entered already. So what I'll do is hit the graph button, and this is not quite correct. So what I'll do to make a really nice window so I can really see the pattern that's happening is hit zoom and then go down to option 9, zoom stat. Makes a perfect window for us. So the polynomial, it looks like it's best going to model this data. Kind of hard to tell, right? It looks like we increase almost exponentially, and then eventually we just have this steep decline right here. So I would say that this looks quadratic or quartic even. I say this because it somewhat looks like a parabola. I kind of go up and then I go back down. If it was a perfect looking parabola, I would definitely say quadratic, but we've got this weird tail right here. Like if I just took out those points kind of on the bottom of this, then I would say absolutely that looks quadratic. Just go up and down. But this tail makes it look a little weird, right? That's why I think it might be quartic too. So for explaining my reasoning, I'll just say it's parabolic in nature. That's a really stupid way of saying that, but hey, it's okay. It's parabolic in nature, but it doesn't perfectly resemble a parabola. Since it does kind of resemble a parabola, that's why I'm saying it's not cubic. Cubic, you wouldn't see a parabola at all. Okay, so that's it for the first page. Again, that was page M2-105. So the second question says to sketch the scatter plot of the data while labeling your axes. So the axes, to label them, you know that the x-axis was the time of day, and the y-axis is the traffic amount. So going to be kind of a hard thing to end up creating. It's starting off at 0. So we could go 0 doesn't really have a place in time of day like how we created it. You know, we started at 1 p.m. So maybe we'll go like this. This is 1 a.m. and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Finally, we get to 1 p.m. That's really where our graph was starting. And then we went to 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m., 7 p.m. And that was the last piece of information that we were actually given. And then the traffic amount, we went from 7,000 was the lowest amount, and then basically 24,000 was the highest. So we can model that pretty easily, I think. It's probably got 20-something squares in this direction. I'll count by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, probably 30, right? 30,000 up here. Okay, so that first piece of information that we were given, it was 1 p.m. and we had 7,000 cars enter and exit the highway. That would be like right here. Then at 2 p.m., we went up to 10,000 cars. At 3 p.m., got all the way up to about 14,000. Somewhere about right there. 4 p.m., went to 21,000. That was a really big climb. Where I'm at now, 5 p.m., we went all the way up to 24,000. And then finally, we started to drop back down. At 6 p.m., we dropped down to 19,000 cars entering and exiting the highway. And at 7 p.m., we went down to 10,000 cars. Okay, so pretty weird looking function there. And that should look pretty similar to what we got over here. This one, it kind of started its scatter plot at 1 p.m. That's why it looks a little bit more flat than mine. So I started our x-axis at like 12 a.m., right? 1 a.m., 2 p.m., so on and so on. Okay, so difficult. Well, actually, we'll just do question 3 first. So use technology to determine the regression equation for the average number of vehicles entering and exiting downtown. Sketch the regression equation on the coordinate plane in question 2. How well does the regression equation model the data? What's your prediction about the type of polynomial that best fits the data? Correct. So to determine the regression equation, we'll go to Stat, scroll over to Calc, and let's do quadratic first. You don't really need to change any of those things. Just go down to Calculate. And there we are. That's our regression equation with an R-squared value of 0.8349. So I actually want to list out some of that stuff. So if it was quadratic, for our quadratic equation, we've got negative 1.364. I'll just round to the nearest hundredth on all this stuff. Negative 1.36 x squared plus 12.16 x minus 6.12. That is our quadratic equation. with an R-squared value of 0.835. All right, so for the quadratic equation, it probably is going to look kind of like this, I would assume. Comes up and kind of hits some of these points. Eventually it reaches this peak, and then it's going to just climb back down. I don't know for sure, but that's probably what it's going to look like. You can graph this too. So if we go back to stat and then over to calculate, we did that quadratic equation. We can actually store the equation that it calculates and graph it later on, which is going to be pretty helpful. So to do that, there's this button down here that says vars. So if you click on it and then scroll over to y vars, we are storing the function, and we'll just store it in y1. So now if I hit y equals, there we go, there's our function. So if I go to graph this time, it'll actually show us that parabola. So I was kind of right, kind of wrong. It didn't actually go through this point, like I said. It didn't actually reach the peak though, which is what I kind of anticipated. And it went a little bit further to the right than I thought. So now let's try something else. Let's go to stat, over to calculate. And then remember we said, well, since it's kind of like weird looking down here, a quartic regression might work a little better. Again, I'll store this one. So I'll go to vars, y vars, we're entering a function. And let's put this one in y2. I'll go to calculate and get all of this information. All right, so here's our quartic regression equation. We go quartic. The quartic equation, so we're doing 0.02. I should probably say y equals 0.02, or 0.03 if I round, x to the power of 4, minus 0.85 x cubed, plus 5.93 x squared, minus 9.5, plus 11.61. I forgot to put an x on my 9.5. Okay, so pretty long equation there. And I just got all of these coefficients from my calculator. I also want to jot down this r squared value. R squared value is equal to 0.985. Okay. Notice that this quartic regression that we did, the r squared value is higher than this one. That means whenever I graph this, hey, just before I do that, remember if I hit y equals, I can see those equations. So my quadratic equation is going to be the blue line. My quartic equation is going to be the red line. So let me go to graph and let's just compare. So here, there's our quadratic equation. There's our quartic equation. So just by looking at that, you should determine this quartic regression did a lot better. It much more accurately predicts the amount of traffic for each given time of day. It even correctly predicted this one, and this one up here too. This one too. Very, very, very accurate. So was your prediction correct? Mostly. The quartic regression was much more accurate. The quartic regression is much more accurate. The quartic regression did very well. It did this little loop, came up, kind of hit most of these. That's pretty well what it looked like. So that quartic regression did very, very well. All right. Let's move on to the next page. See what kind of questions they're asking us now. Maybe I'll make one more point. To really pick which type of function is best, calculate the regression equation and compare the r-squared values. So just for one more example here, if I went down to cubic regression and I calculate this, gosh, that is very high as well. Not quite as high as the quartic function. So the quartic is still best, but the cubic actually did better than the quadratic function. Its r-squared value is higher than this r-squared value. So to really pick the best type of function, we need to compare the r-squared values. And that's what this box is saying. Compare the r-squared values. Whichever one has the value closest to 1 is going to be the best type. Okay, so we're actually going to finally use this regression equation. Downtown is congested when more than 20,000 vehicles are on the streets and highway. Predict when the downtown will be congested. So the downtown area is going to be congested anytime we're above 20,000 on the y-axis. Here's where I made our graph earlier. So hey, here's that line at 20,000 vehicles. It looks like it's going to be congested. It's going to have more than 20,000 vehicles at around 4 p.m., maybe like 3:45 or so, up to, yeah, maybe around 6 p.m., a little bit after 6. See, our predictions are going to be right up here. And it's in between these two times. So for this part A, maybe between 3:45 to probably around like 6:15 p.m. How did I know this? That was where the graph is at least 20. Where the graph or the function is at least 20. Predict the hours when the number of vehicles to enter and exit is less than 10,000. So for 10,000, oops, that's the wrong graph. For 10,000, that's down here. Looks like that happens here at about 2 p.m. And then we're at fewer than 10,000, not until 7 p.m. So between, maybe I should say actually to answer that question. Gosh, I'm getting confused where I'm at. Hey, so before 2 p.m. After 7 p.m. And again, I figure that out just by reading the graph. Predict the number of vehicles that enter or exit downtown during the hour starting at noon. So how we built this was using the time. At 1 o'clock, we predicted 1,000. So what we're doing now is just pretending that, what if it was noon? So we're actually going to take this down to 0. How many vehicles are we predicting when it's noon or like 0 p.m.? Just look at your equation. If I plugged in 0 for all of these x values, we would spit out 11,000. If I plugged in 0, like 12 noon would be 0 in terms of what we did here. So anything times 0, 0, 0, 0, 0, 0, 0, we would eventually get to about 11.6 thousand cars. 11,600 vehicles. To predict the number of vehicles that enter and exit downtown during the hour starting at 9. So there's a couple different ways that we can do this. What we can do is just plug in 9 for our function. If we kept this function going, instead of stopping at 7, we stopped at 9. That's one way we could do it. So, trying to think the best way that I could do this for you. So maybe if we go to stat and then back into our list, we can make L3 equal to Y1. No, we put our quartic function in Y2. I need to give it the variable. Maybe we'll just do this. We'll graph it. And our x values will go all the way up to 10 this time. So there's our prediction line. Looks like it's not even showing up. So we're going to be at a very, 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 very low amount. Really what you're doing, though, is just in that equation that we had built previously, all you're doing is replacing all of these x values with 9. So you would just be evaluating y equals 0.03 times 9 to the power of 4 minus 0.85 times 9 to the power of 3 plus 5.93 times 9 squared minus 9.5 times 9, and then finally plus 11.61. That's all you have to do, is just evaluate it at whatever x value it's giving you. So it shouldn't be too difficult. I'll let you do that on just by your own. The rest of these questions are not really going to apply for us too much. So I'm going to wrap up the video there. It's probably been a long watch at this point already. But hey, thanks for watching. I'll see y'all in class. Bye-bye.